Hey, everybody, and welcome back to Hackaday Remoticon. Our next talk is Maurits Fennis. He's been an artist, a composer, an architectural designer. He's kind of like a lot of us, a jack of all trades. What he's working on right now is reducing e-waste through reverse engineering, and he's here to talk to us about his project. This is something that I think is kind of vitally important as we throw so much good stuff away, but it's often locked up and we can't get into it. So I'm super excited to see this talk. And welcome to the Hackaday Remoticon, Maurits Fennis.
Hey, everybody. It's wonderful to be here. It's an honor to be amongst all of you. And I look forward to speaking to you. I'll share my screen for a moment. Right. So this talk is called Hack for the Planet, Reverse Engineering Embedded Systems to Reduce E-Waste. Like has been mentioned before, I'm Maurits Fennis. I'm a hacker and reverse engineer. I've previously dabbled in architectural design and music, multimedia installations, and I've been active for about 20 years. I am the founder of Unbreak, which is an e-waste reverse engineering laboratory in Belgium, in Antwerp. It was founded in 2020, just before the pandemic. And we collaborate with recycling and refurbishing companies to reduce the global rise in e-waste. In Belgium, there are quite a few initiatives, especially in Flanders, that specifically focus on reducing e-waste. That is Vlaanderen Circulair, Agoria, and Cirrus, and we all work with them, and they're wonderful partners. Now, just to get a quick overview of what e-waste is, I think I am with the right crowd, that you obviously know what e-waste consists of. It is usually discarded electronics, TVs, computers, phones. We could name a lot more, and these are usually dumped elsewhere in large sites. Now, what are the causes of the global rise in e-waste? Is primarily overconsumption. The short lifespan of electronic devices. We know that when we buy a phone, it would only last about 2 years. Any other device you can think of usually has a very short lifespan. Planned obsolescence. Manufacturers make sure that your device dies so you can buy a new one from them, or they will make your device obsolete with a newer version they've produced. The inability to repair. Now, the right to repair movement is very active these days, so I think you've got the message there. Abandoned software support, end of life status. I think we know about this. The destruction of unsold products. We know Amazon is kind of guilty of doing this frequently. The non-adherence to environmental standards, poor waste management, and resulting in illegal dumping and processing. Now, I'd like to focus on overconsumption. If I've read a lot of literature regarding this topic, and what comes up frequently is that richer countries tend to consume a lot more electronics, and then as soon as we are done with them, we dump them in poorer countries. So overconsumption, I think, is the main cause. Well, the GESP released the Global E-Waste Monitor of 2020. And in that Global E-Waste Monitor, we found that each person produced about 7.3 kilograms of e-waste each year. That results in 53.6 million tons of e-waste. And the most surprising figure I found is that only 17.4% was properly collected and recycled. This means that 82.6% of generated e-waste had an uncertain destination, which means that we don't know where it went. 8% thereof is discarded in landfills or incinerated. And as you can see in this image, this doesn't follow any health guidelines or environmental guidelines. And 7 to 20% is exported illegally. Now, the majority is mixed up with other waste streams, and that ends up in the informal sector of less developed countries, where they are traded, burned, dumped in landfills, and kind of endangering the health of people that process this waste and ultimately the environment at large. Now, there are a lot of ways we could solve this issue. There are a lot of different strategies. There are a lot of collective organizations and collectives that focus on policy, try and get some political influence. There are companies that try and make devices that can be repaired. There are organizations that focus more on the humanitarian aspects. But all of these initiatives focus on scale. There's a strong awareness of the scale of the issue and try to address the scale primarily. What we do at Unbinary is that we try and do this in a grassroots approach. Most of you have labs. Most of you have know-how, and most of you are extremely talented. I have been on Hackaday since 2012, and I've seen all of your beautiful artworks. And so there's all of this talent that is there to solve this issue, and all this know-how that can be shared. And at Unbinary, we thought, what if we create very simple tools that we can open source and then share with this community and see what this community does. Also, we learn a lot from you. All of these projects that you are doing with retro systems really inspire us. And we thought it would be fun to make tools that are so simple. They don't require a lot of maintenance, don't require a lot of programming, and could just be used simply. One of them is the Oyster. The Oyster started right before we were a reverse engineering company. I was doing independent security research on a smart meter that had EFM32 microcontroller, and that got me more interested in ARM microcontrollers. So I tried to remove that microcontroller and put it on a small breakout board, but obviously it doesn't have any decoupling, and that will turn into a nightmare. So I thought, why not build my own board so I can do proper analysis? So I reached out to a company in China, and they sent me a few of these QFP48 sockets that I needed at the time. In the left of that image, you can see the pins, and you can see that already that could be quite a nightmare to route. So that turned into this spaghetti. This eventually took a while to do properly. Also, when it comes to doing a power analysis and glitching, making sure that that runs okay. And that turned into the Oyster. It's an STM32L5 target board for salvaged MCUs. So what we mainly use it for is that if we get e-waste and they happen to have microcontrollers with this footprint, we could remove them and place them in here. We use it for debugging and glitching. Power is through USB-C, a coin cell, or external PSU. It has a 48-pin breakout near the top. I think you can see that. And it has 5 debug headers. Now you might be wondering, why would you put 5 debug headers if one standard ARM debug like STDC14 should be enough, right? Or a 10-pin. Well, we have a lot of debuggers here in the lab, and I've kind of gotten used to using several different debuggers for different purposes in the same session. And usually when I'm working, it's a bit frantic, like an artist. I was trained as an artist, which means I'm super messy. And this means that I would like to work quite fast. And that means I just wanted all the headers there, so I didn't need to think about it and just continue working. It has 6 SMA connectors, which connect to the LSC clock, the HSC clock, and the power plane for power analysis and glitching. And it has several jumpers, so you can bypass all of the connectors, and solder jumpers in the back. It has 3D printed magnetic feet, so the device stays on your bench. It's kind of useful because the socket tends to pop open and flip the board. You don't want the microcontroller to fall out. The backside has artwork, and that artwork has a little bit of an idea. That artwork is the face of Paul Feyerabend, which is a philosopher I grew up with, whose work against method I discovered back in 2003 when I was studying music and fine art in The Hague. I'll get back to him in a moment. We created his face with a halftone effect. That is a script we wrote in NURBS in Rhino 3D, where each grayscale value controlled the diameter of a circular NURB surface, and that would create that effect. Eventually, we used SVG2mod to get that into KiCad. So this is where he is. This is Paul Feyerabend. He's a philosopher of science, and he didn't coin the term, but he's known for his epistemological anarchism. And that basically means he had strong critiques of the scientific method and the culture that surrounds science. In a way, when I read his literature, I recognize the hacker in him. He questions absolutely everything, and especially science. And at the time, I was also studying mathematics for a while, and the culture at the university I didn't feel that connected with. So I left, and I stuck with the artists. And he kind of reminds me of a way of thinking that is important these days, where we question our first principles of the axioms we use to do work, do research, and live, if we want to make sure that we don't do much harm to the planet. Now, that questioning I would like to shortly apply to a dictionary term of what it means to be a reverse engineer. Usually when I speak to other people and I explain that I'm a reverse engineer, I get a description that is similar to this one. Recently I spoke to somebody and they said, corporate espionage. And that's not at all what I'm used to doing. And so if we remove those aspects, right, we only get to the disassembly and the examination and the analysis and the discovery of concepts that are involved in the manufacturing of a device. But we can even reduce that further. We could say, who cares about products or devices? Who cares about manufacturing? Reverse engineering is about examining, it's about curiosity, it's about discovering concepts. It's about thinking philosophically about what you have in your hands. That's also what makes praxis different from practice. Now, if we analyze devices you need probes. And during the pandemic, it was very hard to find probes that suited my needs. So I created the first version of the Unbreak probe, which is a silly name, but I stuck with it, which is basically magnet wire, a header, and a spring-loaded needle, and a 3D printed case. And as you can see on the left, it's thick enough so you can hold it in your hand. And I created a little arm that allows you to place it on a PSB so it will stay put. Now, eventually we went through about 7 or 8 iterations for this. And one of the problems I constantly encountered was that the pin, the initial travel distance wasn't that long, and that the pin would be lifted from the board because there was no weight holding it down. So I was trying to find different ways to make sure that its usage was reliable. So eventually we went to a PCB format for it. So it's got, and near the tip, it's got a passive spring-loaded needle probe that's in a receptacle. It's got a 2-pin header, high-frequency SMA connector, 2 solder jumpers, 2 pads for 0402 sized SMD components. And it's got soldered jumpers near there. And the spirit needle can be removed from the receptacle and replaced with concave, convex, and serrated heads. We designed it this way because I sometimes needed decoupling capacitors there, or I needed an LED just to see if there's anything there, so I could kind of play around with it and be flexible with it. Most probes that I had didn't allow me to play around with it that much, so we wanted to do that with this one. As you can see, the pitch is quite slim. It's got a 1.27 millimeter pitch and a 2.65 millimeter travel distance. That means that the travel distance is long enough so that when I push it down, it'll stick. And the pitch is kind of important in combination with a slim, long neck. While developing this, I found that there are other companies that also make similar probes, but I found them quite bulky for my use. The boards that we usually deal with are either very large or very small, and the pitch that we need is a lot smaller than what the heads of those probes would allow. We're currently at version 0.2. This is the one where we will start open sourcing it from December on, so you can build your own. Also, we have prototypes available for free. So if you contact us, we could just send them in an envelope if you pay for shipping. We've improved the VFNs because it needed some improving. We've added curved traces, and we did the SMA footprint to spec because it wasn't before. It was an error that we had. Now, obviously, you don't use one probe while you are working on a board. You probably need more, and depending on the board you have. So we built a base, the Unbreak Pro base, which is magnetic, which has 12 SMA connectors, a 12-pin header in the back, and a prototyping area for 0603 size SMT components, ground buses in the prototyping areas so you can be flexible, and the possibility to bridge SMA connectors. The bridging of SMA connectors was kind of important for us and to be flexible. Also that, because we tend to work in mysterious ways, and sometimes we just need to do that. We use hand-formable RF SMA to SMA cables. They're quite expensive, but they're useful. You can use anything you want. The Pro base has a small footprint, and that is because usually when we're working, and we worked with other probes before, the bench would get full quite quick, and we just wanted to make sure that we didn't use as much space on the bench And this allows us to work in a very kind of lean fashion. It has 10 small magnets on the magnetic base, so it doesn't move. Now, I made a little mistake, and this is again about working in nonlinear ways. I forgot the ground pin on a 12-pin header prior to production, which is a very silly mistake. And I'm a dad, so I was probably tired. So I added one, and which created an L shape, and decided to apply the same operation to the prototyping area. So now it looks like the prototyping area is kind of bleeding to the forward, to the front of the pro base, and we decided to add that to the silkscreen art. I think you can see that in the left image here, where he decided to continue that bleed. Now, having those two helped us a lot with two particular projects that we had. During the pandemic, our budget wasn't that large, and we needed some equipment in order to do our work, but we find quite old equipment that we could use that was either half broken or partially working. And we used these tools on those two devices, which I will show later. We've also created the Unbreak when we got mobile phones in. Just like the Oyster, it is a QFP based design. It's for QFP 48, 64, 100, and 144 pins. It's 3.2 by 3.2 centimeters. It's got a VCC bus on the top edge and a ground bus on the bottom edge. That is so you can bridge to the relevant pads with solder, and on the bottom you can add decoupling capacitors where you need them between the bus and the pads. On the bottom, it's got a prototyping area for 0201 sized SMD components salvaged from mobile phones. And I experiment with this a lot. As you can see, we also have a lot of prototypes of these available. Send us a message and we'll send them to you. As you can see here, we've got the pinouts of the different footprints that are combined here. So the orange one is the 144 pin one. The blue one is the 100 pin. 64. The egg yellow is the 64 pin one, and the light orange one is 48. This is, by the way, documentation you can find on our wiki. We update the wiki regularly. So once we've open sourced all of this, or you've received one from us, you can consult our wiki and find this documentation. Now, when it comes to application, obviously, these tools are still quite limited to what you might want to use it for. The usefulness is quite limited. These tools, however, have been developed within all of them within a few days, and we hope to create more tools. So we have a large set of open source tools that you can use for reverse engineering e-waste, and that you can consult our wiki and our soon to be opened GitLab repo if you ever need any tools to reverse e-waste. Also, if you have any ideas on how to use these tools differently, we would love to hear from you. Now, we've used these tools internally for our little IBM info window. I needed a monitoring tool. I didn't have much around, and I still had this. So made sure it worked again. We used the probes for this. And with these probes, we got this working again. Whereas before it was laying on the ground, and now it's working. We use this really old logic analyzer a lot. It's a very comfortable tool to use next to RDS Logic Pro. But personally, I find this way more comfortable to use. It wasn't fully functional, and we were able to create our custom firmware for this device. And now we use it daily. So that's kind of it. It's a kind of a shorter talk than I expected. If you have any ideas on what you would like to use these tools for, if you have any ideas on which kind of what kind of e-waste you commonly encounter and you need help with reversing, we'd be willing to talk to you, and very willing to talk to you and help you out and create tools that you might be useful to you. Our website is unbinary. Our wiki is unbinare.be, and you can follow us on Twitter at unbinary. Thanks.
Hey, thank you. That's fantastic. Those are absolutely beautiful tools. I'm totally, there you go. Now I'm back. Those are absolutely fantastically beautiful tools. I'm shocked at the kind of the broad range of them you guys have got already. Do you take submissions from other people if other people are working on kind of similar open source tooling? Are you open to looking into it?
Yes, the more the merrier. Having been a lurker for a lot of years, and seeing the amount of talent of people that are on Hackaday, I would love to see what people think and be open to suggestions, but also to designs. We'd love to collaborate with everybody.
Yeah, those probes are
what these are for.
Yeah, those probes are fantastic, and I love the idea of like the multi-probe board with all the SMAs on it. That's really, really sweet. I also think that I forgot the ground layer because I'm a dad and I was kind of tired is the best excuse I've ever heard. That's pretty fantastic. Well, thank you very much, Maurits, for doing this. It was a really great talk.
Thank you. And thanks to the community. Thanks for inviting me.